Hello and welcome to the 27th lecture in this series. So let me, having described a bunch of examples of submanifolds arising from the regular value theorem, now let's talk a bit about their tangent spaces. We have already seen how that the tangent space of a submanifold can be naturally regarded as a subspace of the tangent space of the bigger manifold. Let's use that to describe the tangent space to a regular set, a regular value, level set of a regular value. So tangent spaces to level sets. Well, so the setup is that I have f theorem f from m to n is a smooth map. And then q in n a regular value of f, and then the claim is that and of course p in s equal to f inverse q. So S is the level set, which is a submanifold. So then I want to describe the tangent space to S. It turns out it's exactly equal to the kernel of df at P. So dfp is actually a map from TPM to TQN, and the kernel of this will be a subspace of TPM. So we are describing the tangent space to S as a subspace of TPM, and so we have to use that earlier observation that one can regard the tangent space to S as a subspace of TPM. So let's do that. So the thing here is that in the statement of this theorem, the tangent space to S is already regarded as a kernel of is regarded as a subspace of TPM. But recall that earlier the way we got the tangent space to S as a subspace of this is via the inclusion map. We have seen earlier that the inclusion map I from S to M induces an injective linear map di at the point P from TPS to TPM. So in short, here when I say TPS at this point, I'm thinking of DIP of TPS as the image of TPS under this inclusion, derivative of the inclusion map. Now in fact this way of looking at it will help us see why this statement is true in the first place. So I have a map, so let me use black. So I have a map, the inclusion map I is from here to M, and then I have the map F to N. F composed with I is the constant map. In fact, the whole thing S is being taken to Q. So therefore, since it's a constant map, its derivative is 0. df, now I takes P to P again, so df at P of composed with dip is the 0 map, in particular dfp of, if I look at the image of this, TPS, this is 0, the 0 subspace. So this immediately shows that, therefore, dip of TPS is contained in the kernel of DFP. On the other hand, the dimension of this, we already know that the dimension of this is TPS is n-1, which is also the dimension of DFP. Well, not quite. No, here I'm not dealing with hypersurfaces, so it's not n-1. Rather, it is dimension of so this is dimension of the target n minus dimension of this. The first equality is because we are applying the regular value theorem, and therefore we get the dimension like this. The second one is just that, again, simple linear algebra, that DFP, this DFP here is a surjective linear map. Therefore, the rank nullity theorem tells us that the kernel, dimension of the kernel is dimension of the image minus dimension of the domain. So both are the same. Therefore, this implies that dip of TPS is actually equal to the kernel of this map. So this is a very useful thing, as it turns out. So examples. Let's revisit all those examples of submanifolds. The first one was the case of f from Rn plus 1 to R, and Q a regular value for f is equal to f inverse Q. The level set of corresponding to Q, which is a hypersurface in Rn plus 1. Right. Now in this case, let P belong to S. According to what we just discussed, the tangent space to S is now the kernel of DFP. So the kernel of DFP would be set of all V such that DFP V is 0. Now in this particular case, DFP is a map, linear map from Rn plus 1 to R. So in other words, it's as a matrix, it is just a, well, it depends on it's a 1 by n. So del f by del x1 at P del f by del xn at P. So as a matrix, it's just a row vector with n plus 1 actually, not n. Now, this is DFP. DFP acting on V would be just summation del f by del xi at P Vi, where V equals V1, V2, Vn. And of course, when we think in matrix notation, this would be a column vector rather than a n tuple like this. What we get is this is equal to, so we have this. Now the point is this can also be written as the gradient of f at P in a product with V, where gradient of f at P is again the same thing what I had here, except that I don't think of it as a linear transformation now as a matrix, but as an as a vector. I think of it as a vector with the same entries. Xn plus 1 at P. So in short, with this discussion, this is set of all V in Rn plus 1 such that the gradient of f at P in a product with V equal to 0. So one reason for writing it like this is, let's take the case of the sphere. So take, for example, f of x is norm x squared, as we have been considering. And well, f of x is norm x squared. In this case, grad f at P would be 2p1 2pn plus 1, which is the same as 2 times p. So the gradient of f at P is just P itself up to a constant multiple of 2. So therefore, the tangent space to the Sn plus 1, if I take the regular value q equals 1, so I'll get S equal to Sn plus 1. The tangent space would then be set of all V in Rn plus 1 such that I can forget the 2. Anyway, it's equal to 0. P in a product V equal to 0. This is the tangent space at P, and which can be kind of expected. If you have a point on the sphere, the set of all the tangent space is precisely all those vectors which are, if you think of the vectors as, actually you move the tangent space. If we want it to be a vector space, we would have to think of it as passing through the origin, in which case you will get all vectors which are perpendicular to this given vector P, which is what I have here. But in fact, this is more generally the same thing holds for any hypersurface given by a smooth function like this. Now let me move on to the tangent space to the orthogonal group TAONR. Again, so this time the map was, recall that we had a map from MNR to what I called SN, the group of symmetric matrices, the group of symmetric matrices, and the derivative at A turned out to be AH transpose plus HA transpose. Now, in fact, in the context of this, the orthogonal group and the special linear group, it turns out to the important thing is the tangent space at identity. And so let's look at that. Tangent identity belongs to ONR, and I want to look at the tangent space. And the expression for the derivative here is just, there's no A anymore, H plus H transpose. So this is set of all H in MNR such that H plus H transpose equal to 0. In other words, this is exactly the space of skew symmetric matrices. So the tangent space to the orthogonal group consists of skew symmetric matrices. Similarly, if I look at the tangent space to the special linear group, this will turn out to be, so the derivative in this case at identity turned out to be just the trace function. So this is set of all H in MNR with trace H equal to 0. So one has very concrete descriptions of tangent spaces. Or when we start with a regular level set of a regular value. Right. Now, let me quickly describe the proof of the regular value theorem. So what I'll need a small lemma for this. So here, before I state the lemma, let's recall that the setup was I had a map from here to here, and I took a regular value Q and proceeded to do and proceeded to look at the level sets corresponding to Q. So lemma let P belong to M, and suppose that DFP from TPM to TPN is surjective, i.e. rank DFP equal to M, the target. Suppose then there is a neighborhood U of P such that DFP has rank M for all, well, let me use a different, it's not DFP anymore, DFX has rank M for all X in U. So in short, if the differential is onto at a single point, then it will be onto in a neighborhood of that point. And the proof, now as usual when one talks about the derivative, the statement is purely local. So in short, one can work with coordinate charts, transfer the map f to the coordinate charts and then prove the statement there. So enough to check this when M and N are open sets in Rn and Rm respectively. Oh, I did not add respectively since I did not give any notation for this. Open sets in no, it's okay. Open sets in. Well, open sets in this. Right. Now let's look at, since the good thing about moving to Euclidean space is that now the derivative can be thought of in the classical sense, and in particular I have a matrix, the Jacobian matrix associated to DFP. Since rank DFP equal to M, there exist M columns in the derivative, which I'll use the classical derivative, I'll use capital DFP, which are linearly independent. Remember that this is a matrix of size M cross N. It has N columns and M rows. So there are some linearly independent columns. Suppose let's take some columns. Let's pick out the linearly independent column. Del F M divided by del xi1. This is one column, dot dot dot, del f1 by del xim, del fm by del xim. So these columns are linearly independent. Here everything is evaluated at the point P. So the fact that these are linearly independent would mean that then the matrix, if I just put these columns together, the full Jacobian matrix DFP had more columns. Now I just pick out M of these and put them together. So let's call this columns as A1, AM. So here A1, AM. Then this matrix has non-zero determinant. So if I now here P was already fixed to get these columns, but I can vary P and look at the same matrix and look at the determinant function. So I'll get a function on defined on that open set, and if it's by continuity of that function, after all we are assuming everything is C infinity, so all the partial derivatives are continuous, determinant is continuous. By continuity of that function, by continuity, so let's put A1 instead, in fact let's call it A1 of P here AM of P. By continuity, so this is A1 of P, AM of P. By continuity, even if I change it to some x, AM of x, in other words, I just evaluate the derivatives at some other point x. By continuity, det of this is not 0 for all x in some neighborhood of P. Now let's go back to the full Jacobian matrix. Since in that full Jacobian matrix, this A1, AM are all certain columns. So the fact that this determinant is non-zero will mean that these columns are linearly independent. Therefore, the full Jacobian matrix at the point x will have rank m as well. So this completes the proof of the lemma. Now, once we have that, that is the main point in this proof actually. That's the other thing is the actual, well, that's not the main point, that's a small observation. The actual thing which we are using is the constant rank theorem. So by the constant rank, now that we know that rank is constant, by the constant rank theorem applied to F restricted to U. Recall that this U was the open set around P on which DF had constant rank M. There exists neighborhoods U tilde of P, V of F of P equal to Q with, as usual, F of U tilde contained in V, and we have diffeomorphisms as well. Phi from U tilde to U tilde 1, C from V to V1. Notice that this, we are all, even though we are already in Euclidean space, the constant rank theorem still gives us some diffeomorphisms. Only after changing by these diffeomorphisms we will have the required form for F. Diffeomorphism such that so that C composed with F composed with phi inverse from U1 tilde to V1 has the form phi inverse of X equal to X1 up to Xm. And this C in this picture, Q was here in N and the C was here. Now, by modifying C, we can assume that there's nothing, I mean, instead of considering C, I can consider C minus C of X minus C of Q. We can, so if we do that, then we can assume that C of Q is actually 0. So in that case, so therefore, right, we have that. Consider now, consider S equal to F inverse Q, the level set, and Y in S. So in other words, f of y equal to q. Well, so this was so f was landing here, this was c. So what I do is I can write y equal to y in S. Yeah. So y was actually, I need another picture. This is M. The set S was here, y was some point here, and phi was going here. So I look at, I can write y equal to phi inverse x. Y equal to phi inverse x. Therefore, f of phi inverse x equal to q, and now if you look at x1 up to xm 0 0 0, this is c composed with f composed with phi inverse x. This is just because the general form that I have here. Actually, I should put zeros here as well. Zeros. Let me leave the bracket. Yeah, put lots of zeros there. So because of this general form, I have this, but on the other hand, f of phi inverse x equal to q. So therefore, this is c of q, and I've assumed that c of q is 0 here by changing q, changing c if needed. So the upshot is that, right. So this is equal to 0. Therefore, x1 equal to 0, x2 equal to 0, etc. xm equal to 0. So what has all this accomplished? It's just that, therefore, phi is a slice chart for phi is a slice chart for S. Right. Phi is a slice chart for S, and except that the only difference is that when we say a slice chart, we wanted the submanifold coordinates to appear in the first few places and zeros to follow that. Here we are getting the opposite. We're getting the submanifold is getting taken to points in Rn plus 1, rather Rn, where the first certain number of coordinates are 0 and the last ones are variables. So that one, again, one can change phi, modify the diffeomorphism phi so that this last m minus n coordinates, n minus m coordinates will appear in the first. So in other words, except that S is getting mapped to because of what we said here, 0 0 0 x m plus 1 x n. See, this equation that we have here shows that the first m coordinates are 0. So under this map phi, S is getting mapped to this. What we want is, instead of, we want x n minus m followed by zeros. Now if we want S to get mapped to this standard form like this, all we do is we change the slice chart phi by a suitable linear transformation of Rn, which will take the last m minus m coordinates to the first one like this. a sort of permutation matrix will accomplish the job. So let's stop here. Next time I'll make a few remarks about smooth maps into submanifolds and then start a discussion of vector fields on manifolds. Thank you.